All right, so continuing our adventure into type 1 ionic compounds and their nomenclature, that's the fancy word for writing the names and formulas. We're going to talk about polyatomic ions. They're a little bit different just in terms of their structure and what they mean. However, the rules for naming them are essentially the exact same thing. First and foremost, what is a polyatomic ion? We talked about it briefly in the last video, but just to reiterate and go into more detail, a polyatomic ion is a covalently bonded molecule that as an entire group has a charge. Because as a group, it has a strong attraction and it has pulled some electrons from somewhere else, giving it more electrons than it typically would have as a neutral compound. So for example, the two that I used in the last video were CO3 with a -2 charge and NH4 with a +1 charge. Right below each of those compounds here, we see their different chemical structures, and we see that here we do have a covalent compound where there's one carbon bonded to 3 different oxygens. However, 2 of those oxygens each have taken an electron from somewhere else. They didn't share them with the carbon atom there. So because there are those 2 extra electrons, this thing as an entire group has a -2 charge. Slightly different but similar idea for the ammonium. Here we have nitrogen on the right bonded to 4 different hydrogen atoms. However, there's an electron missing from that central nitrogen. There's an extra proton, right, the hydrogen without an electron, present in this compound in order to make this thing bond and work. Now, because those things have an electric charge, they're going to attract oppositely charged particles, right? Coulomb's law. So in the example of CO3 with a -2 charge, it would attract positive ions. So in this case here, with a -2 charge, it could attract 2 different sodium atoms to make it an electrically neutral compound, such as this. Or that -2 charge can attract a single ion with a +2 charge to give a formula such as this. Really, it can attract anything with a positive charge as long as the ratio comes together to make an electrically neutral compound. NH4 over here is one of the very few polyatomic ions that have a positive charge. It's the only one we're going to be working with in this class for sure. There aren't that many, but it can also attract a negatively charged ion. In this case, I actually had it attract a negatively charged polyatomic ion. Here we have this polyatomic ion is an oxygen and a hydrogen with an extra electron, and it is being attracted to this polyatomic ion here, the NH4 with a +1 charge, and those 2 things are coming together and would form eventually a crystal lattice as it grows and grows. In terms of the nomenclature for these, we're going to get all of the rules for them from the back of the periodic table of ions. There's a list of all of the polyatomic ions that we're going to use. They're sorted by the charge that they have. And in terms of their name and their formula, it's all right there. However, every once in a while, you're going to come across polyatomic ions that are not on there. However, their ending, you're going to notice, is very similar to ones that maybe are. Those endings are extremely important, and it's the reason why you need to be careful when you're reading or writing something as to whether or not you're saying something like chlorate or chlorite or chloride or chlorine, because all 4 of those words mean different chemical compounds. For polyatomic ions, and specifically, the ending refers to how many oxygens are in that polyatomic ion, what we call the oxidation state of the covalent compound. So if you come across a compound that is not listed in the polyatomic ion sheet, but its ending is similar, you can use these rules here to help you figure out what the formula is going to be. These rules are also on the back of that periodic table of ion sheet, so you don't necessarily need to recopy them right now, but I wanted to draw your attention to them. When you have a compound that's polyatomic and ends in ATE or ITE, you can use this order and ranking system to figure out what the number of oxygen should be on any of those other compounds, knowing that the charge doesn't change in any of these. In all 4 of these examples, this is all a -1 charge. The only thing that is changing is how many oxygens are in each of these compounds. So if you know wherever the ATE ending is, 1 less oxygen would be ITE, 2 less oxygens becomes the prefix hypo, then the stem, and then the suffix of ite. So in this case, we have chlorate, chlorite, and hypochlorite. If you have an extra oxygen, you would have per as a prefix, and then the stem, and then ate is the ending. In this case, perchlorate. This same rule can be seen on the table for things like phosphate and phosphite and hypophosphite, or nitrate, nitrite, or sulfate and sulfite. In terms of using those and the other endings on the back there to write the names of these, the first thing you need to do is identify what is the cation and what is the anion and split them apart. So we know that the cations are generally going to be metals unless they are that NH4 compound. So here is our metal. We're splitting there. We have a metal with magnesium, and we have a metal with aluminum. All of the monatomic ions are going to be named exactly the same way they were in the last video. So in this case, we have the cation sodium is monatomic, magnesium is monatomic, and aluminum is monatomic. All of those are cations, and we said that the cation name just gets written the way it was. It doesn't change. So we have sodium, magnesium, and aluminum. Then for the polyatomics, we're going to look them up on the back of the paper. We're looking up that formula. So we need to look to see really quick, what is the charge? What is the formula? What are we looking for on that sheet? Well, in this first compound, we had sodium with a positive 1 charge. We have HCO3. And if the charge of sodium was positive 1, then we know that this should be a negative 1 to make that electrically neutral. So we're looking for HCO3 on the back of our periodic table. That has two actual different names. One word that is used is sometimes called bicarbonate. So this formula here is the formula for sodium bicarbonate, also known as baking soda, but it can also be called hydrogen carbonate. Either one would be acceptable. For the second example, we have magnesium with a 2 plus charge. We have SO4 with a negative 2 charge because it has to balance out that 1 magnesium. If we're looking up SO4, not SO3, SO4 on the back of the periodic table is sulfate. So this is magnesium sulfate. And then our last example, aluminum has a 3 plus charge. Now here I have 3 on the outside of parentheses. That means I have 3 of this compound. So my polyatomic ion is OH, OH, and OH. I have 3 different ones. So if I have 3 of those and a positive 3 charge on the aluminum, then each of these must have a charge of negative 1 to balance that out. So I'm looking for OH with a 1 minus charge on the back of my periodic table, and I see that the name of that is hydroxide. And again, from here, we're going to go into a couple more examples and practice and how we can go in reverse if we want to write the formulas instead. So again, we're going to start by looking for the monatomic ions. We have calcium, magnesium, and in our last example here, there are no monatomic ions. Ammonium is not an element. It's not on our the front side of our periodic table. And tartrate, that ends in ATE, that should also tell me that this is a polyatomic ion, because we know that all of those monatomic ones ended in IDE. So all of these remaining ones I need to look up on the back of my periodic table. Carbonate, we look up as CO3 with a 2 minus charge. Phosphate is PO4 with a 3 minus charge. And tartrate is C4, H4, O6 with a 2 minus charge. Ammonium was the example we used earlier. That is NH4 with a positive 1 charge. Just like we had done for binary ionic compounds, we need to make sure that these charges neutralize so that the formula unit we write is neutral. In our first example with calcium and carbonate, we have a positive 2 cation, we have a negative 2 anion. Those two things do cancel out already, so our formula would just be CaCO3, one of each of those ions. For our case of magnesium and phosphate, like we did in the binary examples with things like aluminum and oxygen or gallium and sulfur, we cannot make a 2 into a 3. We need to find a common multiple for each of those. It's going to be 6 in this case. So magnesium 2 plus, magnesium 2 plus, magnesium 2 plus gets me to 6. To get phosphate to 6, I would need 2 of those. So 2 different PO4 ions, which means that my formula unit is going to be Mg3 because I have 3 magnesium ions, and then I have PO4, but I need to show that I have 2 of those, and I cannot put a 2 here because that would be 1 phosphorus and 42 oxygens. I need to show that I have 2 phosphates, so we do that using these parentheses as we talked about earlier. And then in our last example, we have a positive 1 and a negative 2. I would need 2 of the positive 1 compounds to balance that out. So my formula should have NH4, and I need to show that there's 2 of them. And then there's 1 of these tartrate compounds. Okay, and then these are all just more example problems. I would pause and try them, quickly skip through to see what my solutions are before trying the practice work. Here we have Zn. Looking up on the periodic table, it's a positive 2 charge. Chlorine, there are 2 of them, so each one must have a negative 1 charge. This is a binary compound, so zinc, and then we change the second one to end in IDE, chloride. Right, so we have a binary compound here, not a polyatomic. In our second example, we have 2 aluminums. They each have a positive 3 charge. We have 3 SO4s. If the aluminums add up to positive 6, then the SO4s must add up to negative 6, so minus 2 on each of those. So if we look up the SO4 on our periodic table, we should have aluminum as the cation and sulfates as the polyatomic anion. Next, we have 3 RBs. RB is rubidium. From the periodic table, that should be a positive 1. P, we know, is a negative 3 from the periodic table, or because it balances out here. This is a binary compound, so we name this one very easily. Rubidium, which I'm not spelling correctly at all. And then our last one has to end in IDE since it's a binary compound. Example number 4. We have magnesium, and we know that it has a positive 2 charge from the periodic table. And then we have 2 of this polyatomic ion. We know that it's going to need to add up to negative 2 to match the magnesium. From the back of our periodic table with the polyatomic ions, we also know that OH always has a charge of minus 1. So here we have magnesium, and then look up OH1 minus, or if you remember from earlier, that is hydroxide. Going in reverse, we have germanium oxide. So germanium, using the front of your periodic table, is 4 plus. Oxide refers to oxygen, which is 2 minus. I need those charges to balance. Right now I have a positive 4, but only a negative 2. So I need to make them equivalent to each other. I can make this into a negative 4 by getting 2 of those oxide ions. So my formula unit would be GeO2. For calcium, has a positive 2 charge. Nitride refers to nitrogen, not NO3 or NO2. N has a negative 3 charge. Need to get a common multiple of 2 and 3 here. So to do that, I would need to get a positive 6 charge and a negative 6 charge. And my formula unit would be Ca3 and 2. Tantalum is Ta. It's in the D block. It has a charge of 5 plus. Sulfite, ending of ITE, not IDE. That indicates that this is also a polyatomic. I need to look this up on the back of my paper. Sulfite is SO3 2 minus, not sulfate, which is SO4 2 minus. I need to get these into a common multiple. I cannot make a 2 into a 5 or a 5 into a 2. Common multiple is going to have to be 10. So to do that, I would need 2 tantalums, and then I would need 5 sulfites. Gets you Ta2, SO3, and I need to show 5 of those sulfites, so parentheses 5. And then last example, we have potassium, which is K with a positive 1 charge. Phosphate is PO4 with a 3 minus charge. I would need 3 potassiums to balance out that negative 3 charge. Gives me a formula unit of K3PO4.